Welcome everybody to GeoHug. So before we kick off today's session, I'd just like to take this time to acknowledge the traditional lands which we're all coming from today. I live on the beautiful lands of the Gadigal of the people of the Eora Nation, and I'd like to pay my respects to the elders past, present and future. And I'm thrilled to have Armando Simon joining us today. So Armando has 48 years of experience in geological exploration, mining, QA/QC on projects throughout the world with extensive exposure to multiple deposit types. He also has more than 35 years of graduate and postgraduate teaching experience, including QA/QC workshops for more than 3,400 professionals from over 51 countries. So it is going to be wonderful to learn from him today about the control chart conundrum, assessing accuracy or precision. So I hope you all enjoy it. Please use the chat. We'll open up the floor for the discussions at the end. And yes, thank you so much, Armando, for joining. It's amazing having you here.
Thank you very much, Jessica, for your presentation. And thank you also for inviting me to have this talk with our colleagues from all over the world. This is the subject I would like to talk to you about today, control charts. So control charts are a consistent component of every quality control program. And control charts were invented in the 1920s by Walter Sheward. He was a statistician, an American engineer, and he used to work at the time for Bell Labs. So I will go a little bit later into more detail about how he came with the idea of building or preparing control charts. On the other hand, reference materials are used everywhere, practically virtually in every exploration program, in every mine, in every laboratory. So we commonly use these reference materials to assess analytical accuracy. But I wonder, and that's my intention to discuss with you today, if this is actually the actual purpose of building control charts. I have the impression, I will explain that to you later, that the role of control charts is frequently, the actual role of control charts is frequently misunderstood in quality control, in particularly in geological exploration. So let's start with quality. What's the meaning of quality? If we look at the quality definition in ISO Guide 9000 2015, it states that the quality is the degree to which a set of inherent characteristics fulfills requirements. Quality is not quantified, so we can speak about good quality, poor quality, excellent quality. We can qualify it, but we cannot quantify it properly. For quantification, we will use different ways that some of them we will discuss there. I will discuss them later. Process quality, which is actually the field of the quality we are dealing with, is managed through a quality management system. And this system is defined as the part of the organization's management system that focuses on the achievement of results as appropriate. If we intend to design, to draw somehow what is the environment or the extent of the quality management program and its relationship with quality assurance and quality control, we could see that in this image. Typically, quality assurance activities and responsibilities cover practically all the quality system in one fashion or another. But when we speak about quality control, we should understand that it is just a subset of the quality assurance activities. And these terms, quality assurance, quality control, are often also mixed or used interchangeably, which is not adequate. When we speak about quality assurance, what we think about, it is defined as the part of quality management focused on providing confidence that quality requirements will be fulfilled. And an alternate definition is that it includes all planned and systematic activities implemented within the quality system that can be demonstrated to provide confidence that the product or service will fulfill requirements for quality. Notice that I have underlined will be. All the action, all the field of action of the quality assurance is the future. Processes that have not occurred yet. When we prepare protocols, whatever type of protocols, we are working on quality assurance. Quality control is something different, is a subset of that in a certain way, and it is defined as the part of quality management focused on fulfilling quality requirements. If we put it in other words, the objective or the purpose of quality control is assess the degree to which the quality requirements have been fulfilled. Alternatively, we could say that it includes the operational techniques and activities used to determine if the quality requirements have been fulfilled. Notice again that I have underlined have been fulfilled in both paragraphs. So why I haven't done that? Because quality control looks at the past, at processes that have already occurred. And this is actually the main difference, I would say, between quality assurance and quality control. The reports we prepare every month or every week, every quarter or every week, when we discuss the results of standards, duplicates, and all that, they are not QA/QC reports. They are actually quality control reports. So how is quality approached in NI 43-101? And it is roughly the same way in JORC or in SK 1300. So NI 43-101 states that all written information on scientific or technical nature related to mining projects should specify if a qualified person has verified the data on which this information is based, including sampling, assays, and tests. It should describe the quality assurance program and the quality control actions. Look that NI 43-101 distinguishes both activities. It should describe the nature and limitations of the verification and explain any deficiencies found during the verification. Many people, many geologists, and I have observed that in many places, believe that things like the quality control program, like how many samples we should take, how many duplicates should take, are part of a certain indication of NI 43-101, for instance. And there is no indication, not at all, on NI 43-101 or JORC or SKY for 1300 or other codes as to any unique quality control method or procedure. So purpose. Everything we do should have a purpose. And I wonder, what is the purpose of the quality control program? What is the actual purpose? If you ask this to geologists all over the world, a common answer is something like, I have a quality control program to see if assay data are reliable, if the lab works fine, or something like that. Most of the time, the quality control is perceived as something, at the process or an activity meant to assess the laboratory performance. However, the ultimate purpose of the quality control is to determine if the assay data resulting from the exploration program are sufficiently precise and accurate to be used for estimation and classification of mineral resources and mineral reserves. In Australia, following JORC, you would say ore reserves. This is something I learned from Henry Parker. I believe that many of you have probably heard of him or maybe even worked with him. So when I mean here that the assay data are sufficiently precise and accurate and so on, take into consideration that assay data are the result of a comprehensive process that starts with sampling and ends with the assay, and even could extend or extends to the database compilation. It is strange, or it could be odd, that the terms precision and accuracy, which are actually the ultimate purpose of the quality control, those terms rarely appear in quality control reports. And believe me, I am telling you about this because of my experience in virtually all continents, with the exception of Antarctica, and many tens of projects audited in major companies and exploration companies and all that. So let's go. Once we understand that this is the purpose of the quality control program, let's try to discuss a little bit about the concepts so that we have a common understanding when I will mention precision or accuracy, so that we understand what we are talking about. I say that because sometimes these terms are confused, or maybe they are called in a different way in other parts. So how precision would be defined? It is the capability of consistently repeating the results of a certain measurement in similar conditions. That's the simple definition of precision. In order to be able to assess precision, we should maintain repeatability conditions. So when we repeat an operation, the repetition should be conducted in the same conditions as the original operation. When we send duplicates to the lab, or when we take sample duplicates, they should go together until the end of the process in order to maintain the repeatability conditions. If we don't do that, I don't say that it is wrong, but that operation would not allow us to assess precision. Accuracy, which is actually the core of what we are going to discuss today, is defined as the proximity of a certain measurement to a supposedly real or conventionally accepted value. Why real is under such marks, I don't remember how they are named in English, because we never know what's the actual value or the actual grade of the sample, or the actual value of a measurement. There is something always, whenever we extend it with more decimals, it will continue, or we'll never know exactly what's the actual value. Contamination is the third concept that I would like to mention, which is not much discussed, which is not much subject to confusion, but it would be defined as the inadvertent transfer of material from one sample or the environment to another sample. What we are going to assess during the quality control is actually the experimental uncertainty. And this uncertainty is mainly due to two types of errors: random errors and systematic errors. Random errors can be defined as statistical fluctuations in measurement results. They are produced in any direction due to limitations in precision of the device, the sampling process, or the analytical method. So when we speak about precision, we are thinking or dealing with random errors. These errors result from the incapacity of the operator or the equipment to repeat exactly the same measurement in such a way to obtain the same result. That's what we understand by precision. Systematic errors are accuracy deviations. Generally, they occur consistently in the same direction, usually result from the persistence of a problem during the entire experiment. If we look at the frequency of the occurrences of systematic or random errors, both of them are systematic. So they will always occur. There is no way to escape from random or systematic errors. There is no way. We could minimize them if we follow adequate protocols or so, but it is virtually impossible to eliminate them. They are inherent to any measurement process. However, sometimes there are other errors that can occur, and those are the mistakes. Mistakes occur when there is an incorrect application of the work protocols. You mix the sample numbers, you mix the bags, you mix the code of the standards. Those are mistakes. And when such errors occur, they should not be considered in the analysis of the experimental uncertainty. And the simplest way to distinguish what precision and what accuracy represent are shown here. The 4 alternatives. This yellow guy has good precision, so he's able to repeat consistently the shot every time he does it. The blue one has a low precision. His shots are spread. He has a higher variability. Both of them are far from the center of the whatever, I don't know the name in English. In this other case, both of them group their shots around the center of this. What's the name of this, please?
It's like target?
Yeah, the target. Okay, the center of the target. Thank you. But the yellow one is more precise, and the blue one is less precise. But both of them, if you look at the center of all their shots, they more or less go close to the center of the target. So in this case, both of them have high precision, but the yellow one is high accuracy, but the yellow one is more precise, the blue one is less precise. Here, both of them are very poorly accurate. Let's design an experiment to assess accuracy. And we should start from the definition. So the definition of accuracy, what we have seen before, is the proximity of a certain measurement to a supposedly real or conventionally accepted value. So what kind of experiment we could design to assess accuracy? We will take, if we look at in particular in our case, we will take a sample whose value we know more or less with a high probability. These are the reference materials. And when we include a reference material, when we insert a reference material, a standard, in a batch, and this standard is assayed together with the other samples in ordinary conditions, and when we compare one with the other, the ideal value with the ordinary value, we can determine if the lab has overestimated or underestimated the value. So this is the way we assess accuracy. We assess accuracy at the same laboratory when we insert reference materials or standards in the batches. And we should do that in principle anonymously, which is something that I don't believe, because very often we send to the lab 100-gram bags or something like that, or 200-gram bags, or 20-gram bags, together with 8 or 10 kilo samples. And what lab will not understand that this is a standard? So anyway, but the theory says that we should try to do that anonymously. We should standards of different nature to the material that we are going to assess. We should use various standards in order to assess accuracy at different levels of range. And when we try to quantify the accuracy, we have a problem, because accuracy is not a quantitative parameter. Accuracy is a qualitative parameter. We can say that we have obtained low accuracy, high accuracy, acceptable accuracy, but we cannot say that accuracy is 5%. For that, we use a quantitative parameter, which is the bias. The bias is calculated as the average divided by the best value or the recommended value of the standard minus 1 expressed in percentages. If the bias is positive, then we could say that the lab, for this particular element whose bias is positive, we can say that the lab is overestimating the grade of the element, of whatever element or analyte. If the bias is negative, then we can conclude that the lab is underestimating the value of the particular element. This is the way to quantify the accuracy. what could be conventionally accepted criteria. And this might be different for some of you, but in the company where I used to work and where I was actually formed as a specialist QA/QC, we considered that the bias was okay, was acceptable if it was between -5% and +5%. It would be questionable if it was between +5 and +10 or between -5 and -10. And unacceptable if the bias exceeded 10% or was below -10%. This is a convention. So we might agree on that or not, but at least we use that convention. However, whenever we purchase or we request or we order a standard, a reference material, there will be in the certificate a value, which my colleague Scott Long used to call best value, or could also be named suggested or recommended value. I will continue with the best value term. And there is also an indication about the confidence interval, the 95% confidence intervals. What is the meaning of that 95% confidence interval? I will discuss it a little bit later, but for the time being, let's assume that it is something it can be understood as the error of the best value. So if this is the best value, let me see, I hope that you can see my pointer. If this is the best value, and this is the confidence interval around the best value, if my average, so the average of the samples I have, of the standards I have submitted to the lab, is within this field, then we say that the bias is not measurable because it is within the error of the best value. So this is probably the kind of control chart that most of you or many of you have seen in the past, or even prepare now. I can tell you that the overwhelming amount of people of companies I have worked with, the geologists I have worked with, they do this kind of control chart. What are the main elements of this control chart? A center line, which is drawn around the best value. So this corresponds to the best value of the standard. There are also here control limits, best value plus 3 standard deviation, control, so best value minus 3 standard deviations, and the standard deviation is obtained from the standard certificate. This is the most common way of preparing this control chart. And this is exactly what I want to discuss with you. Walter Sheward invented the control charts. Why did he invent the control charts? At that time, it was in the 90s, in the 20s, the last century, they didn't know the kind of miniaturization we are able to obtain now when we build cellular phones or computers. So the communication equipment they built in the Bell Labs were so large that many times they buried them in the ground. And whenever there was a problem with any of them, they had to unbury them. So Sheward understood, he was an engineer working in that company, that it was essential to reduce the frequency of failures because it was a mess when they had to repair something that was in the ground. He also understood that whenever we do continuous adjustments, we observe that there is a problem and try to modify the process, to adjust the process. It actually increased the variability, and then it had a negative impact on the quality of the process. So he tried to focus in his research about reducing the variations during the manufacturing instead of doing that after delivery. In his studies, he concluded that in every process of every kind, there are variations. Some of the variations can be controlled, can be expected, they are inherent to the process, and then he called those variations of common cause. And there were also other variations that were uncontrolled, that did not occur all the time, and he named those variations of special cause. So essentially, he, in order to understand how those types of variations occurred, he designed the control chart. Actually, the control chart was something that he did it. The design, the description of a control chart was one page, and half of that page was the control chart itself. So he believed that if the production could be kept in statistical control, what was statistical program? When only common cause variations are present. So the process, if the production or the process can be kept in statistical control, then there is no need to modify it, to adjust it. We should simply let it go as it goes. On those conditions, it is possible to foresee what will be the future outcome of the process and handle the process within economic conditions. So Shewhart's control chart is defined as this. In a control chart, data should be plotted on a time sequence. That's what we do whenever we build a control chart. The control chart has always a central line, and that central line should correspond to the average of the process data, the center of distribution of the process data. And a control chart will also have lower and upper control limits, and those limits should be established on the basis of historical process data. I would say that the main aspect of the core of Shewhart's thinking regarding the control chart is that the control chart should be process dependent. Dependent on what process? On the process we are assessing. When we compare the actual data with the control lines in the control chart, then we can determine if a certain value, a certain point, a certain in the plot corresponds to a common cause, or if we find some variation that corresponds to a special cause, and then the process is out of control. Whenever the process is maintained within the control limits that we have established or we will establish, then we say that the process is in control, and we better don't touch it. We have only to think about modifying, about implementing some actions, some correction actions, in the case that special causes variations appear. So this is the plot I showed to you a few minutes ago. And I wonder if this Shewhart's control chart, so the center line of this plot is the best value. So it was plotted here, considering the recommended value in the standard certificate. And the standard deviation we see here is the standard deviation taken from the standard certificate. And I wonder if this Shewhart's control chart, is this the control chart that Shewhart invented in the 1920s? No, this is not Shewhart's control chart, because the plotted lines are based on data from another process. What process? The round robin that was done for documenting the standard, I don't know, maybe 1 year ago, 5 years ago, 6 years ago, whatever. So this is not Shewhart's control chart. And this is what we usually prepare, or most commonly, I could say, geologists not from Chile, not from Peru, not from Ecuador, from all over the world. And I tell you because I have been practically all over the world, and I have audited many reports, I have discussed this with many people, and this is the kind of control chart that most geologists believe that is correct. But this is not Shewhart's control chart. This is Shewhart's control chart. So the central line of the control chart should be the average of the values, and the upper and control limits should be established on the basis of the standard deviation of the values we are assessing here. There is no room, there is no place in the control chart, in Shewhart's control chart, for the suggested or recommended or certified, as some people say, which is not strictly certified value from the standard. There is no place. You don't see here is a line corresponding to the certified or recommended value. But this plot is correct. This chart is correct because it is process dependent. On what process? On this process. What is this process? The assay of the standards in the lab I use for assaying my samples. So now look at this. We have in this chart, we have one sample which is out of control because it is above the upper control limit. With the same distribution of values, if we would have prepared this control chart, we would have now 6 out of controls or apparently out of control samples. And this is what happens when we build a wrong control chart. Let's try to understand actually what the control condition means. So when we say statistical control or simply control, what is the actual meaning of that? And we have here 2 cats, a big one and a small one, in what could be something that we would not be surprised to see in them. They are showing a behavior that would be for us normal, in control. We would say that a cat, small cat, looking like this one, is in control. Cats are usually inoffensive. I have a cat at home, so I know this very, very well. And this is something that if you mess with a lion, you would not be surprised to observe this kind of reaction. This is normal. In these 2 situations, both the lion and the cat could be considered in control. That's the normal behavior for them. These are out of control situations. A cat rarely becomes aggressive. It may happen. In that moment, he is out of control. It is out of control. And a lion kissing the guy, it is completely out of control. This is not normal for the lion. And look at this. What could be in control for a lion would be out of control for a cat. What could be out of control for the lion would be in control for the cat. So the control condition is adequate for every process. Every process has its own control condition. And let's see again this image. So we could say that the yellow shooter is pretty much precise. He shoots 4 shots, and all of them are very close to them, or to one to another. The same with the blue one here, the yellow one here. Those are precise shots. They might be far from the center of the target, but they are precise. But this one, the green one, corresponds to the blue shooter, and the red one corresponds to the yellow one. Those are imprecise shots, out of control shots. So if I ask the blue guy to shoot another shot, it will probably fall somewhere here. Rarely it would come somewhere here, because this is his control, this is his comfort position. So it will be somewhere here. The same with the yellow one. So these are in control shots, so precise shots, even if they are inaccurate. And these are unprecise shots, even if this one just by chance lands in the center of the target. This is also an out of control shot. Okay, let's see what most of you or many of you are Australian, and you probably know ROC-Labs. So I will read you some scripts from a ROC-Lab standard certificate. This says certificate of analysis, reference material, whatever, recommended value, so that the best value, as Scott Long used to call, the 95% confidence interval, and it says somewhere in the first or the second page, Neither the standard deviation nor the confidence interval should be used as basis to set control limits when plotting individual laboratory results. Exactly what most of geologists and chemists do. A little bit later, it says, we quote a 95% confidence interval for our estimate of the declared value. This confidence interval reflects our uncertainty in estimating the true values for the gold and silver content of the reference material. The interval is chosen. What interval? The confidence interval is chosen such that if the same procedure as used here to estimate the declared value were used again and again, then 95% of the trials would give intervals that contained the true value. That's actually the true meaning of the 95% confidence interval. It is a reflection of how precise, oh, wow, look at this, how precise the trial has been in estimating the declared value. It does not reflect the variability any particular laboratory will experience in its own repetitive testings. It continues. Some users in the past, and I would say in the present, have misinterpreted this confidence interval as a guide as to how different an individual test result should be from the declared value. Some mistakenly use this interval or the standard deviation from the consensus test to set limits for control charts in their own routine test results using the reference material. Such use inevitably leads to many apparent out-of-control points, leading to doubts about the laboratory testing or of the reference material itself. This is what I have shown you here. In a proper control chart, we have one out-of-control sample. In the wrong control chart with the same values, now we have 6 apparently wrong or apparently out-of-control samples. And let's finish with Rocklab's statements. A much better way of determining the laboratory performance when analyzing the reference material is to accumulate a history of the test results obtained and plot them on a control chart. The appropriate center line and control limits for this chart should be based on the average level and variability exhibited in the laboratory's own data. This chart will provide a clear picture, and to help Rocklab's customers, they offer in their webpage an Excel file which prepares exactly those control charts we have been discussing about. So, not only Rocklabs, you have probably heard of Bureau Veritas. And there is a document from Bureau Veritas definitions and guidelines for the interpretation of quality control, which states exactly the same. I will not read it. Whoever might be interested, I can send after that. I will send this presentation to Jessica, or I will also give you my contact data. So if somebody is interested, I can send you this document. But it says the same thing. When referring to the standard certificate, neither the 95 confidence interval nor the standard deviation quoted in the certificate should be used to calculate control limits or to fail a batch of samples. The American Association for Quality, ASAQ, they also, some of the references I have shown here, and you have seen that in many slides, there is a reference below so that you could go to the reference in the internet. So they also include a template. This is just part of the template that can be used to prepare proper control charts. And there is a set of links in the internet that can serve you to understand better what I have been explaining, because this is something I have not invented. How control charts are prepared, and this is the ASQ's recommendation. We select a certain period. How long could be that period? I remember that when I started to work in Antamina 5 years ago, they at that time used 1 full year. Then I said, okay, it is too much. let's consider 6 months. And after a few months, we decided to go to 3 months. And this 3-month period is moving all the time. So if I am going to process the September data, I will calculate the average and the standard deviation from September, August, and July data, and so on. So we establish a certain period. Data corresponding to that period are then selected and plotted in a time sequence. Then we plot the central line and the control lines, using the central line, the average of those values, and for control chart, for control limits, the average +2, +3. There are different ways. I will talk a little bit about that a bit later. So we will plot the control lines too. And then we analyze the chart. If there are potential out of control limits going outside the control limits, then we should investigate them and see what the causes are. If one of those aspects or issues corresponds to a special cause, maybe we have to produce some kind of action, something that could be eventually to repeat a batch, but not necessarily. And at the beginning of the project, when I don't have enough data, well, I start using what I have. And after I have 20, 30 data, then I already recalculate the control limits and redraw my control chart, and then I continue from then on. So why do we use control charts? We use control charts to control how the process varies in time, to know to identify the different eventually out of control points, to determine if the process is stable, so if it is in statistical control, to predict variations in the future, to evaluate patterns of variation due to common causes or to special causes, and to determine if at some point in time we should introduce corrections to the process or significant modifications in the process. When we establish our control limits by average ±2 or ±3%, this has an implication, a quantitative implication. Within the boundaries, within the limits, the control limits established as average ±3%, we include there, or they are included, nearly 99.73% of all the data. If we consider 2 standard deviations, ± 2 standard deviations, then it includes 95%. How do we identify if we have an out of control event? There are different ways to do that. I am showing here, and you could see it in the presentation when you receive it, one which is common for everybody: a single point out of the ±3 deviation control limits, it can be considered out of control. 2 out of 3 in the case of ASQ, 2 out of 3 consecutive values between average +2 and +3, or between average -2 or -3, or below -2 or above -t. 2 out of 3. And there are other ways. You could check them. Here is the description. There are also the Western Electric rules. Shewhart used to work for Western Electric, and they had a full set of rules. But in our case, actually, what we would discuss, what the rules I commonly use are simpler, are just the first 2 ones of those ones, and are coincident with Bureau Veritas recommended rules. Whenever we find an out of control event, is this necessarily a special cause event? Not necessarily. This is a normal distribution between the average -3 and +3 standard deviation. We will have 99.7% of all the values, but still there could be common cause events that have a very low probability that would fall, for instance, here or here. So not necessarily an out of control event would have to be qualified or named a special cause event requiring eventually an action that could be, for instance, repeating a batch. But we have here, let's go to the title of our presentation, the control chart conundrum. There are some apparent contradictions in everything I have told you. We use control charts, and the control limits in the control charts are determined on the basis of standard deviation, +2, +3, -2, -3. But standard deviation is not an accuracy-related parameter. Standard deviation is related to variability, so to precision. Standard deviation is a precision-related parameter. And I wonder what would be the purpose of preparing a control chart to assess accuracy if the control limits are established on the basis of precision-related parameters. There is something here that it is not easy to understand. What the answer would be, the control chart was not conceived by Shewhart to assess accuracy, but the control conditions of the process. So actually, the control condition of the process is related to precision, not to accuracy. In our case, assays. We normally use in our control programs duplicates to assess precision, not standards. But when we have 100 standard values, we actually have 1 original and 99 duplicates, because a standard is a duplicate of itself. So we can use also standards to assess precision instead of, in addition to duplicates, because we can measure the confidence, the coefficient of variation of the values of the standard. And if this coefficient of variation is low, for instance, below 5%, that's a reasonable value, then we can say that the standard was assayed in good precision conditions. So what can we use then the control chart for assessing accuracy? No. We can only assess accuracy when we calculate the bias. This is actually the assessment of the accuracy. If we don't say that during the month, September, the lab has overestimated the copper value in 5%, we have not assessed accuracy. We have prepared control charts, we have spent a lot of money, but the only purpose of using standards at the end is to establish if the lab is overestimating or underestimating the grades and to what extent they are doing that. So we can only assess accuracy whatever the amount of standards we use in the program, whatever the money we use in the program for assess, how many control charts we prepare, we can only assess accuracy if we state the value of the bias and the sign, because it's important. So if that's true, why do we use control charts? We use control charts just to identify out-of-control events. Those events, those out-of-control events, should be excluded from the assessment of the bias. So this is the bias formula, and this average is the average of the values we obtain in our process, in the process we are assessing, but excluding the out-of-control points. It doesn't mean that we ignore whatever happened when we had an out-of-control point. We should investigate it, and then maybe we should find the solution later. But when we calculate the bias, initially for the month we are assessing, we should determine the average of the precise values of the standard, so those within the control limits, and use this formula, and then we will have the bias. If we don't do that, I am sorry, but we have not calculated, we have not assessed the accuracy. And this is the way I determine the out-of-control values, which is more or less what Bureau Veritas does. This red line here is the average, my average. So the average of these points, not something that I have extracted from the standard certificate. This blue line, just for reference, I included in my control charts, but this blue line corresponds to the standard recommended value. So this is the average, 2 plus 3 standard deviations, plus minus 2, minus 3. The standard deviation is the standard deviation of this set of values during the period I am assessing. If I have one value alone above the average plus 3 or below the average minus 3, this is an out of control point. If I have one isolated value above the average plus 2 standard deviation, not reaching the 3 standard deviation, I will accept it. This is okay, this is okay. But if there are 2 consecutive values above the average plus 2 standard deviations or below the average minus 2, then I consider both of them as out of control. Would be any real difference between 2 plots, 2 control charts, one wrong and one correct? This is the difference. I have put the same data in those 2 plots. This is a wrong control charts, and now we have all these apparently out of control points. When we prepare the correct control chart, all these disappear, these ones too, and there are other ones appearing here, one here, and one here. So this is actually the implication of preparing or building a correct control chart. What do we do? And we finish with this when we have non-conformities. I will mention this is a table from my course, my workshop. So in principle, I will just go quickly and we'll stop a little bit more with the standards. In all cases, the first step in processing the quality control data is determine if we have course mistakes, possible mistakes, possible mix-ups, mislabeling. And for this, I use a method that I call the DNA test. DNA that I compare the values of the different elements. The more elements, the better. And I actually implement here a pattern recognition process. So all the standards of the same type will have roughly the same pattern. If I find something which is completely different, then I may assume, or I can demonstrate that or it is another standard, or it is another sample that was mixed up. In the case of duplicates, my recommendation is never repeat a duplicate failure. I could not extend here on the explanation of this. If somebody would be interested in discussing why, I will give you at the end my contact data, and we could arrange a meeting to discuss that. But believe me, repeating duplicate failures is the equivalent of using a net to transport water, to take out water from the sea. In the case of the standards, my recommendation would be to repeat some standards to determine, and some neighboring samples, not necessarily to order a repetition. Why that? In every measurement, there are 2 components, a random component and a systematic component. So a certain value at some point in time, the value of the standard may be out of control due to eventually very low probability random errors that could appear, but will only affect the standard, not the rest of the batch. If it is random, it will only affect the standard. Or it could be related to a systematic error, and in that case, the systematic error will affect the entire batch. So before ordering the lab to repeat a batch complete, I prefer to determine first if the error is a random error or if it is done due to a systematic error. And I do that by ordering the repetition of 4, 5, 6 samples, the standard, the failing standard, and 2 or 3 around. What happens if the repetitions is like this? So let's assume that this is a standard. and then when it is repeated, it is out of control. So I repeat these samples, and I notice that now it is within the control limits. But what can I observe? This value has lowered. This one has increased. This lowered. This is the same. This is lower. This is higher. So the problem we had is it was a precision-related problem. It only affected the standard. There is no need to request the repetition of the batch. On the contrary, if I observe a pattern that all samples lower, even if it is not in the same proportion, or all samples go up, then the problem that I am facing, that I have detected, might be most probably an accuracy problem. And then in that case, if it is sufficiently strong, then I may order the repetition of the batch. So thank you for your time. Maybe there are some questions, but in case any of you would like to discuss these issues in more detail, you will find here my WhatsApp number and my email address. Thank you very much.